So in this session, we'll see how to solve a truss or analyze a truss by using a direct stiffness method. This is the example of a truss, what has been shown over here. So if it has to be analyzed using the direct stiffness method, and the area of all the members are same, and modulus of elasticity is given as E. So the truss has been supported at joints A and B with hinge supports. At C, there's a load of 25 kilonewton acting in downward direction, and at D, we have a load of 10 kilonewton here. So the length or the horizontal dimension of truss is 2500 mm, whereas the height of truss is 3000 mm. Now, first is what is the degree of kinematic indeterminacy of this truss or degree of freedom? So we have 4 joints. At each joint, we come across 2 degrees of freedom, one horizontal translation and one vertical translation. So 2 into 4, 8 will be the degree of freedom. But in this case, we have supports being provided at joint A and joint B. So there will be restraints provided here. So these 2 joints are not allowed to translate in any direction. So I have to deduct these 4 restraints which have been provided imposed on joint A and B. So totally what we end up is we'll come across finally 4 as our degree of freedom for this truss, which are translation at C and D. Now coming to the numbering of elements and nodes. So what we have is there are 6 members in the truss. So this was the truss over here. This is how the members were arranged, and these members represents the element over here. Each member of the truss will be considered as one of the element, and for each truss element we have 2 joints, 2 ends, and at every end there will be 2 degree of freedom. Okay, now numbering will be done and in this for all the members, so that itself will represent the element numbers. So here it has been numbered 1 to 6 for these members. Now numbering of node has been taken up here. So the nodes or the joints where the translation exists, which are free to translate either in x or y direction, have been numbered first, and later the restrained degree of freedom have been numbered. So joints 1 to 6 we have 1 to 4 we have here 1, 2, 3 and 4. So at joint 1 and 2 what we have is the degrees of freedom have been restrained because there were supports which were provided at joint A and B. So the joints A and B were this 1 and 4 over here. At joint 2 and 3 we can have a translation in x and y directions. So the numbering of the coordinates have been started with these joints. So these represents the local or elemental coordinate what have been given here. So at joint 2 coordinate number and 2, 1 and 2 have been given, and at joint 3 coordinates 3 and 4 have been assigned. Joint 4 the coordinates 5 and 6 have been assigned here, and at joint 1 the coordinates 7 and 8 have been assigned. So you are free to choose any order of numbering as per your convenience, but it is better you fix up some order. Here what has been done is the joints which are having freedom to translate have been numbered first, or actually the coordinates at this joint have been numbered first. Then the joints at which the degree of freedom have been restrained, at these joints the coordinates have been numbered later. Okay, so this is how the order has been followed in this example. So this is an individual truss element. So these are the degrees of freedom that exist at the 2 ends of these element. One horizontal translation, one vertical translation, and at this end also one horizontal translation and one vertical translation can take place. So this is what you have, and all of these members are representing such elements over here. Okay, so they may be inclined at any angle with respect to the global x-axis, right? So this is the element numbering and even the coordinate numbering. We have 6 elements which correspond to 6 members of the truss, and they have been numbered here. And coordinates at the joints have been identified. The coordinates for the joints where degree of freedom exists or which are free to translate have been numbered first. Later, the joints where restraints have been provided or where supports have been provided have been numbered later over here. That is how it has been, this numbering has been followed. Now we'll go for developing the stiffness matrix for each of the elements. So what stiffness matrix will uh, develop here, or what stiffness matrix we are going to write right now in this will be the direct stiffness matrix, or it will be a stiffness matrix with respect to the global coordinates. It will be an element stiffness matrix but with respect to global coordinates. So this is the relation what we have for developing the element stiffness matrix in global coordinate. So here the stiffness matrix for any element in terms of global coordinate can be written by knowing its cross-sectional area, modulus of elasticity, and the length of that member. So this ratio A by L multiplied by this matrix, this rotation matrix over there. Now this rotation matrix consists of the C square, Cs, and S square terms over here. So C stands for the cos theta here, S stands for sine theta, whereas Cs stands for cos theta sine theta. This is simply cos theta. So that is what this matrix will be containing: C terms, C square terms, S square terms, and Cs terms. So C for cos theta, S for sine theta, Cs for cos theta into sine theta. This theta will be the orientation of the member which we are considering, for which we are writing the element stiffness matrix. So accordingly we will be choosing what is the value of theta and the values of A and L and the modulus of elasticity. So let us apply this for each of our elements. I'll be applying this matrix, this relation for each of the element in this truss, and we'll develop the element stiffness matrix in the global coordinates with respect to the global coordinates. So in this, if I take the first member, so first member, what was the first member here is this member, what is here. So this is numbered, this vertical member is numbered as number 1, first member. This is AC. So this member AC has been numbered as member number 1 or element number 1. Okay. Now what coordinates are there with this member are 1, 2, 7 and 8. So if I take out this member from this truss, what it will be having is at this joint 1, okay, there are two coordinates 7 and 8, whereas at joint 2 there are two coordinates 1 and 2. Okay, so here that coordinates have been written over here while developing this element stiffness matrix. 7 and 8 at joint number 1, 1 and 2 at joint number 2. Similarly here also these are the numbers which represents the coordinate numbers at the two joints of the element. Okay, now length of element, the height of truss was given 3000 mm, so this is 3 meters. What is the angle with respect to the global x-axis? So it was vertical member, this theta is 90 degree. Now if I take this trigonometric ratio for 90 degree, cos theta c comes out to be 0, cos theta into sin theta will also be 0, whereas sin theta will be 1. Okay, so we'll be taking those cos square sin square theta in this. So this will be cos square theta, this will be cos theta sin theta, and this will be cos theta sin theta, and this is sin square theta. Okay, this is divided by L. So L has been taken, this length of member has been taken inside 1 by L into sine square theta. Sine theta is 1, so sine square theta remains 1. So 1 by 3.3333, that is recurring, so that has been considered over here. So cos square theta, cos theta sin theta, cos theta sin theta, sin square theta, and in this minus cos square theta minus cos theta sin theta minus cos theta sin theta minus sin square theta. This will be minus cos square theta minus cos theta sin theta minus cos theta sin theta minus sin square theta, and here cos square theta, cos theta sin theta, cos theta sin theta, and this is sin square theta. Okay, so always follow this matrix, rotation matrix, for the truss element. Okay, so this is the matrix what I have applied for developing the element stiffness matrix over here for member number 1. So I have obtained this element stiffness matrix for the first member, member 1. Okay, now coming to second member. Okay, so the second member is here. This is a horizontal member here, so that will be second member. So theta for this will be 0. So the value of theta is 0, and L is 2500 mm, or the length of the member is 2.5 meters. Now for this value of theta equal to 0, cos theta will be 1, cos into sin theta will turn out to be 0, sin theta will be 0. So again what I'll be going is, I'll be taking this relation of element stiffness matrix for the truss element, which is given by AE by L, into this matrix containing these terms of cos square theta, cos theta sin theta, and sin square theta. Okay, so I'll be using the values of these trigonometric ratios, and I can obtain the element stiffness matrix over here. So L have been multiplied here. So 1 by 2.5.4. Okay, here it is cos theta sin theta 0, cos theta sin theta 0, sin square theta. So this is 0, and in this quadrant minus cos square theta minus zero point 0.4, cos theta sin theta 0, cos theta sin theta 0, sin square theta 0. So this will be same as that of this values in this quadrant what we have. Again here this will be cos square theta sin, cos theta sin theta, cos theta sin theta, and sin square theta. So in this way I can write the stiffness matrix for the second member. Similarly, we'll be using the same matrix relation for writing the stiffness matrix for member 3, 4, 5, and 6 over here. We have totally 6 members. I'll be applying the same relation of the matrix for these over here. So by doing that, you'll be able to obtain the stiffness matrix for all the 6 members in global coordinates. If you take the member 5 and 6, they are the inclined members in this truss. So this value of inclination with the global x-axis is 50.19 degrees. On calculation you will get it as 50.19 degrees. So you can take the tan ratio of this opposite and adjacent sides. You will get to know what is this angle theta over here. So now what coordinates are there with member 5? So member 5 is this inclined member. At one end you have the coordinates 7, 8. At the other end you have the coordinates 3 and 4. Okay, so 7, 8, 3 and 4. 7, 8, 3 and 4. Similarly for member 6, at one end the coordinates are 5 and 6. At the other end coordinates are 1 and 2. Okay, so 5 and 6, 1 and 2. So these are the coordinates over here. So here the length comes out to be 3.905 meters. Angle, as I told, on calculation you will get it as 50.19, so 19444 degrees. So taking the ratio of cos of this angle, sine of this angle, we'll be able to write what is cos square theta, so cos theta sin theta product, and sin theta. So on substituting in that rotation matrix, we'll be able to get this stiffness matrix. The member length has been divided for all of these 2 point, that is 3.0905 meters. Okay, so this will be the stiffness matrix for member number 5 and for member number 6. So this is the way in which we can directly write the stiffness matrix, element stiffness matrix, in the global coordinate. I have made use of the relation what we have and I can write this element stiffness matrix with respect to global coordinates here. Okay, now how do I write the entire global stiffness matrix? This have to be assembled now. Okay, so the global stiffness matrix, in order to get this global stiffness matrix K. Okay, so the global stiffness matrix. So what I'll be doing is I'll be arranging all the stiffness coefficients in this global stiffness matrix, but look for these coordinates. In what all member stiffness matrix there are common coordinates. Say for example I want to write this the first coefficient of this global stiffness matrix. So what I have is, when I come to the member 4, I have the coordinate 1. Okay, and coordinate 1 is present in this member number 6. So these are the two members in which coordinate 1 has been shared over here. Okay, now what is the value of stiffness coefficient in this member 4 for coordinate number 1? So look for 1 1. Okay, 1 1.4, the value is zero point 0.4. And there is also a coordinate in member 1. Coordinate 1 is also present in member 1. Okay, so here 1 1, what is the value here? It is 0. Okay, 0 plus, in this it is 1 1. Okay, so in this member 4 the value is zero point 0.4, so 0 plus zero point 0.4. Okay, plus in member 6 what we have is, so 1 1 k11, that will be 0.1049. So 0 plus zero point 0.4 plus 0.1049. This is how we get this global stiffness matrix. Okay, so similarly, if I go for this second one, okay, this will be one. So the value what is here is, it will be k21. Okay, if I add up 210 here and 210 over here, similarly 21, it is minus 0.1259. Okay, 0 plus 0 plus minus 0.1259, this is the value what is coming over here. Okay, k22, if I want to obtain the stiffness coefficient, global stiffness coefficient k22, so 22.333 here in the first member. Member number 2, it is we don't have a second coordinate coming over there. Similarly member 3 also is not sharing any second coordinate. Member 4, what we have, 220. Okay, and here it is 0.1511. Okay, so what we had here was 0.333 plus 0 plus 0.1511, so that will be 0.4844. This is how you need to obtain all of these elements of the global stiffness matrix. Okay, so this will give us the global stiffness matrix of 8 by 8, because 8 degrees of freedom were there, 4 joints and 2 degree of freedom at each of the joint. So we come across 8 degrees of freedom for that truss. So this global stiffness matrix will come out to be 8 by 8. Okay, now what happens in this problem here is, in 8 degrees of freedom, supports have been provided at the two joints. So this support, what we have is hinged support. They were hinged support. So they are not allowing any kind of translation over there at those joints. At the joints 3 and 4, if I come back over here, the joints 1 and 4. So at these two joints, or at A and B, hinge support were there. So at joints 1 and 4, there will not be any translation. So these degrees of freedom have been arrested. There is no displacement taking place in coordinate 5 6 7 and 8. So the displacements in these coordinates 5 6 7 and 8 are 0. So evidently I don't require these rows and columns corresponding to the coordinates 5 6 7 and so I can eliminate the rows and columns corresponding to the displacement, or 5 6 7 and 8, these degrees of freedom. In this stiffness matrix I can eliminate these 4 rows as well as the 4 columns, because we know what is the condition at these joints over here. So that is 0, so we don't require them. On doing that, what finally we end up is P1, P2, P3, P4. Okay, so these are the only forces what we need to evaluate over here. So the displacements what we have is u1, u2, u3, u4. These are the displacement at node number 1, sorry, at the joint number, at the two joints where degrees of freedom were not restrained. So on solving this equation, okay, so what is this P1, P2, P3 is? These are the joint forces, the forces which are directly applied at the joints. So here we have a load of 25 kilonewton applied at in that second coordinate in vertically downward direction, but it is the direction of this force was opposite to the direction of the coordinate, so minus 25. P3, this is the force which is applied in the third coordinate. It was 10 kilonewton towards right, so this is 10. And in first and fourth coordinate, no forces were applied, so 0, 0. Value are 0, 0. Okay, now rearrange these and find the inverse of this matrix. And if we go for calculating the displacement at the four coordinates 1, 2, 3, 4, at these coordinates, we'll be able to find what are the displacement that are occurring in these coordinates. So these are the values of the displacements what we have. Okay, if a and e values are known to us, then further we can multiply this and these values with 1 over ae, right? So this is the solution for the displacements. Using these displacements, now I can go for finding the support reactions. So what are the support reactions? The reactions over here, they are at these two joints 1 and 4. So we need to find these forces corresponding to coordinate 5, 6, 7 and 8. So P5, P6, P7, P8. So at these joints, what forces are developed? They are nothing but the reactions of the supports. So P5, P6, P7, P8. So that can be obtained by the same relation K into delta. P is equal to K into delta. Here it is U. U and delta, they are representing the displacements. Okay, nodal displacements or the joint displacements. So I'll use this matrix from 5 to 8, row number 5 to 8, column number 5 to 8, this part of the matrix multiplied by the displacements what we obtained earlier, u1, u2, u3, u4. So that will tell us what are the reactions at the supports or the forces in these particular coordinate. So P5 is the force in this fifth coordinate, which is at this joint over here where one of the support is provided. So this is the reaction, horizontal reaction, minus 7.5662, means it is directed towards left. That is one reaction. Similarly, the vertical reaction at this support over here at this particular joint, it is 12 kilonewtons, and at joint A the horizontal reaction is 2.4338 kilonewton and the vertical reaction is 13 kilonewton. So that is the support reaction, how we get them. Now the member forces, for calculating member forces, the relation what we will be using is this A by L into CS minus C minus ES into L by E into the displacements what we have obtained. Okay, so this will give you the force in each of the member. If I take the first member, so there already we have calculated the values, trigonometric values, cos theta and sin theta. So that will be A by L. Okay, so into this, this is cos theta divided by L, sin theta divided by L, minus cos theta by L, minus sin theta by L, these values into the U matrix, the displacement matrix, what we have. So at one end, okay, so U1, U2. So at the near end, these U1, U2 represent the displacement at the near end. Okay, U3, U4 at the far end. Okay, if you consider the joint at A as the far near end, so far end will be having the values of displacement what we have obtained earlier. It is not directly the values what U matrix is here in the previous one. So here the okay, so this is the degrees of freedom, the displacement what we obtained corresponding to the coordinates 1, 2, 3, 4. Okay, now when it comes to finding member forces, here I am talking about the coordinates for that respective member. U1, U2, U3, U4 are the coordinates for that respective member, which I had shown in this figure over here. Okay, so for that one individual member, these are the U1, U2, U3, U4 values. Okay, so for first member, here support is provided. So here we have U1, U2 as 0, U3, U4 are the displacement what we got on after solving the equilibrium condition. Okay, similarly, if you take member number 2, both ends have been supported. Supports have been provided at the both ends. So U1, U2 as well as U3, U4 remains 0. Okay, third member, U1, U2, they are 0. U3, U4, they will be taken from the solution. So what are the displacement at these coordinates? We have solved for that. So that will be coming in that matrix over there. So on multiplication, we will get the member forces here. So member 1, it is carrying a force of 15.919 kilonewton and it is tension. If it is coming out to be positive, this value, it is tension, else it is compression. For second member, that is that horizontal member which is between the two supports, so the force is 0 in that member. The third member, the force is 2.921 tension, and similarly for the rest other members 4, 5 and 6. So here we are getting the values in negative, indicating that they are in compression. Okay, so take care that what are these displacement. U1, U2, U3, U4 represents the displacement for that individual member at the two ends. Okay, if at all, if any end is having support, see what degrees of freedom have been restrained over there, and accordingly set these values to 0, or at the other end check it from the displacement matrix what we got from the solution.